Hi everyone. In the last video, we looked at a number of examples of sequences of functions and determined in what kinds of different ways they converged or failed to converge. From that, at the end of the last video, we were able to start hypothesizing some relationships between the different kinds of convergence. In this video, we want to address those hypotheses to see precisely which types of convergence imply some of the others, and to see further what additional conditions we might need to impose to get relationships between the various types of convergence. So I want to begin by actually just sort of giving you the answer. So you can see up here, I have sort of the 7 different types of convergence we've talked about. So from 5610, right, we have uniform and pointwise convergence, and of course, uniform implies pointwise. But now we have proceeded to add the almost everywhere versions, right? So certainly uniform implies uniform almost everywhere, and pointwise implies pointwise almost everywhere. Now, additionally, we have added almost uniform convergence, convergence in mean, and convergence in measure. Now, if you will recall, last time we looked at sort of this collection, the uniform and pointwise collection, and sort of saw them as sort of local types of convergence, right? Whereas mean and measure were more global types of convergence. So it's maybe not surprising that there are a lot of relationships over here. There's a relationship over here, and the relationship between these two regions is a little more tenuous, right? So let's talk about a few of these things. So you have sort of the uniform column here, right? Again, certainly uniform implies uniform almost everywhere. Uniform almost everywhere implies almost uniform, right? So how do we prove that? Well, if it's uniform almost everywhere, that means it's uniform except on some set of measures 0. So let's call that set where it's not converging uniformly A, right? Well, then the convergence is almost uniform because for every epsilon, I can choose a set of measure less than epsilon. I'll just choose the set A. It has measure 0, which is less than epsilon for every epsilon, so that my sequence converges uniformly on E delete A, right? So almost uniform almost everywhere gives you almost uniform just straight from the definition. Okay. Now, some of these others, again, we've already proven before uniform implies pointwise. But you can see here, I've also written down that almost uniform implies pointwise almost everywhere. Now, that takes a little more work, right? So here you would need to show the idea really is you have this sequence of sets whose measure is going to 0. So for every epsilon, you have some set on which it's converging uniformly, except on that set of measure less than epsilon. And you need to make some sort of limiting argument so that you essentially show that even though in the limit it might not be converging uniformly, it will be converging pointwise. So that's another option. Now, you can see I have these solid arrows. Now, these solid arrows mean that we don't need any additional conditions. These dashed arrows, right, show implications that are true only if we're working on a domain with finite measure. So if we're on a domain with finite measure, for example, uniform almost everywhere actually implies convergence in mean. Okay. If we're on a set of finite measure, pointwise almost everywhere, it actually turns out you can reverse this. On a set of finite measure, pointwise almost everywhere convergence implies almost uniform convergence. So what we want to spend our time doing today is not memorizing this chart necessarily. This is just sort of here for reference and so that you see some of these connections. But what we want to do is we want to spend some time actually proving a couple of these just to see how some of these proofs work. We'll then look at the theorems that justify some of the others, and then in fact see that there are even further implications if we make even more assumptions. So we'll look at some other convergence theorems that don't actually fit nicely into this diagram. So this diagram really only covers the relationships when you either don't need any additional conditions, or the only condition you need is that your domain has finite measure. So let's begin by first proving that if I have that convergence in mean implies convergence in measure. So going back to this chart quickly, right? We're proving this arrow over here. Okay. Now, in fact, the ones we're going to prove today, right? We'll prove this one first, right? So this is just sort of looking at those global sorts of convergence theorems. We'll then also look at almost uniform convergence implies convergence in measure second. We'll then briefly discuss what is known as Egorov's theorem, right? So we'll look at that third. And then the last couple of things we'll look at are actually sort of arrows that don't exist on here, and we'll talk about why the arrows aren't on here when we get there. So this will at least give you sort of the idea of the order we're going to go through as we prove these today. So the first thing we want to look at is this global result. Now, convergence in mean implies convergence in measure. The converse is not true. We saw, we saw an example of that. So I think the tall spike, right? The sequence of spikes, the indicator function, the set is going to basically 0, but the height is getting higher each time. So that converges in measure, but not in mean, which tells you that convergence in measure cannot imply convergence in mean. But convergence in mean does imply convergence in measure. And so let's take some time to work through the proof of that. So I'll let Fn be a sequence of integrable functions on E that converge in mean on E to an integrable function f. Then the sequence f sub n converges in measure to f on E. Now, the way we're actually going to attack this is we're going to do a proof by contradiction. Okay, so for this, what am I going to do if I'm going to prove this by contradiction? I'm going to assume to the contrary that what? I'm going to assume to the contrary that f sub n converges in mean to E, or converges in mean to f, but that it does not converge in measure. Okay, so to converge in mean means the limit as n goes to infinity of the integral over E of f sub n minus f d mu is equal to 0. And what? Now I want to assume that it does not converge in measure. So I'm also going to assume that the limit as n goes to infinity of the measure of the set of all x in E such that f sub n of x minus f of x is greater than epsilon. I'm going to assume that this limit is not equal to 0. Now, when I say I'm assuming this limit is not equal to 0, I'm really assuming sort of two possibilities. I'm assuming that either this limit fails to exist at all, or it exists and is not equal to 0. Okay. Now, that distinction is important because of what I want to do with this next. I can't just say, oh, well, if the limit as n goes to infinity of the measures of these sets is not equal to 0, then let's assume it's equal to L, right? Because this limit, again, may fail to exist entirely. I don't know. Okay. Now, if the limit does exist, right, it certainly would have to be positive, right? Because it's not, I'm assuming it's not 0. So it would have to be positive because these are all non-negative. Okay. So if the limit exists, it's positive, but I don't even know if the limit exists. But what I know is that if I go far enough out, right, in my sequence, right, I must be able to find some term that gets like at least gets far enough away from 0 that it's not getting closer to 0, right? So said another way, so now let's think formally about negating this definition, right? We have the limit of this is equal to 0. What's the negation of that? Okay, so well, that means that there must exist some value, I'm going to call it delta. So there exists some delta such that I can't find an n beyond which all the values of this are less than that delta. So with that in mind, I can choose. So there exists some delta greater than 0 and a subsequence this is going to be a subsequence of the f sub n's. I'm going to call them f sub n sub k, such that the measure of the set of all x in E such that f sub n sub k of x minus f of x is greater than epsilon is greater than or equal to delta for all k. So again, the idea here is this limit is not 0. Okay, so that means there's some neighborhood around 0 that these values must, they can go inside that neighborhood, but they can't stay inside that neighborhood forever, right? Because otherwise, if they did, and I could do that for every neighborhood, the limit would actually be 0. So there's some neighborhood around 0 so that these values must come out every so often, right? Like in infinitely often, right? So I'm going to pick the subsequence of these to be the values such that this difference, such that the measure of this set is greater than or equal to delta for all these things in the subsequence. All right, now I want to come back to my convergence in mean assumption. And I'm going to need a little sort of setup here to help myself. So by the convergence in mean, I'm going to have that the limit as n goes to infinity of the integral over E of f sub n minus f d mu. That's equal to 0. Okay, so that's just from convergence and mean. But now I'm working with this subsequence. Well, if this limit is equal to 0, then the limit of any subsequence must also be equal to 0. So I can just pass here to the subsequence. So f sub n sub k minus f d mu. All right. And now what I want to do is I want to break this this integral up. The limit as k goes to infinity of, and what I'm going to do is I'm actually going to define, so this set right here, I'm going to call this set A. Okay, so this is just a set of all x values where f sub n sub k minus f is greater than epsilon. So I'm going to break up this integral over E into an integral over A plus an integral over A's complement in E, just A complement intersect E. I'm sorry, that's f sub n sub k and f sub n sub k. Now, if I look at this term, this is sort of the one I don't really care about that much. This is the one I'm not working so much with. So I actually sort of want to throw it away. If I do that, I'm integrating here something that's non-negative. So this integral must be greater than or equal to 0. So if I just throw this piece away, then instead of having equality, I now have this inequality. But now on the set A, f sub n sub k minus f is greater than epsilon. So here you have an integrand that's greater than epsilon. And it's greater than epsilon on this set. The measure of this set A is greater than or equal to delta. So you get that this is actually strictly greater than epsilon times delta. Okay. But now we realize we have a contradiction because I have here that 0 is greater than epsilon times delta, but epsilon and delta were both strictly positive terms. Okay. So this is my contradiction. So my claim that I have convergence in mean but not convergence in measure must be false. Therefore, if I have convergence in mean, then I must have convergence in measure. So this gives you, I mean, A, gives you some insight into the relationship between these sort of global notions of convergence. And also it just gives you a little more experience working with these, maybe now not applying them to specific functions, but looking at how they work in a more theoretical setting. Now, again, so far, we seem to have this sort of the global convergence things in mean and measure. They have no relationship to the more local ones, like uniform, almost uniform, pointwise almost everywhere, those sorts of things. But what we will see in the next theorem is the one connection, right? Namely, we will show that almost uniform convergence implies convergence in measure. Okay. Now, unlike the previous theorem, we're not going to do this by contradiction. We're going to prove this directly. Okay. So if you think about this, what am I assuming here? I'm going to assume I have a sequence of measurable functions that are converging almost uniformly on E. Then I want to show that they have to converge in measure on E as well. Okay. So my goal is to show that F sub n converges in measure on E. So let's think about that for a second. Like, let's do a little sort of pre-planning, right? So I want to show that limit as n goes to infinity of the measure of the set of all x in E such that f sub n of x minus f of x is greater than epsilon. I want to show that this limit, right, is 0. Okay. How do I do that? Well, one way to do that, just using the definition of limit, right, is that I want to show that for every, well, I want to say epsilon, but I'm already using epsilon here, right? So I want to show that for every, well, sorry, if I want to show this, I want to show this holds for every epsilon greater than 0. So then for every epsilon greater than 0, I want to show that this limit is equal to 0. So for every epsilon greater than 0, and we'll say delta greater than 0. Now this delta is playing the role of epsilon for this limit statement. So for every epsilon greater than 0, I want to show that this limit is equal to 0. So for every delta greater than 0, there exists a natural number, capital N, such that whenever little n is greater than capital N, the measure of x and E such that f sub n of x minus f of x is greater than epsilon is less than that value delta. So it's really like absolute value of this minus 0 is less than delta. All right. So this is what I want to show. Okay. What I get to use is that my sequence of functions is converging almost uniformly on E. So this isn't like my proof yet. This is just sort of a restatement of what I want to show. Okay. So let me actually write my proof now, or get started on my proof. Okay. Let me actually go ahead and erase some of this to give us a little more space. So this is what I want to show. All right. So let epsilon greater than 0 and delta greater than 0 be given. Yeah. So I want to prove something for every epsilon and for every delta. So I'm just going to fix them first. Okay. Now, what I have is I have the almost uniform convergence. Okay. So what does that mean? That means that for every epsilon, right, I have to be careful here because this could end up being delta, right? It's actually going to be epsilon in this case. So for every epsilon, so since f sub n converges uniform or converges almost uniformly to f on E. So, and actually, I misspoke. This is going to be for delta. There exists a set, and we're going to call that set E sub delta, such that f sub n converges to f uniformly on E delete E sub delta, and the measure of E sub delta is less than delta. So again, here the delta is playing the role of, if you write down the definition of almost uniform convergence, it has an epsilon in it, but we're using the delta value here for that. Okay. Now, what does that mean? So f sub n converges to f uniformly on this set. So hence, there exists a natural number n such that f sub n of x minus f of x is less than epsilon for all x in E delete E delta. Said another way, on the set E delta, right, this must not be true, right? So, well, let me say, it's certainly less than epsilon here, okay? Let's actually compare, let's write this a different way. So, if I look at the set of all x in E, such that f sub n of x minus f of x is greater than epsilon, okay? It can't happen on this set, right? F sub n of x minus f of x can't be greater than epsilon on this set. It can only possibly happen on its complement, but its complement is a larger set, and the complement of this set in E is just E delta, right? The complement in E of E delete E delta is just E delta. So you get that this set is a subset of E delta. And by monotonicity, the measure of this set is less than or equal to the measure of E delta, which is less than delta. Now this holds for all n greater than capital N, right? So sorry, hence there exists a capital N such that this holds such that when little n is greater than capital N, this holds for all x here. So this is a subset of this, and by monotonicity, this is less than or equal to this, which is less than delta for all little n greater than capital N. So what have we shown now? We've shown that for any epsilon, okay, so fix an epsilon, then for any arbitrary delta, I can choose a capital N such that the measure of this set will be less than that delta for all little n greater than capital N. Well, that means I've shown that for arbitrary epsilon, and hence for all epsilon, the limit as n goes to infinity of the measure of the set of all x in E such that f sub n of x minus f of x is greater than epsilon, and the limit must be 0, because I can make it less than delta for any arbitrary delta greater than 0. So this just means that f sub n converges to f in measure. So this does give you one result, or one way in which this sort of local form of convergence, almost uniform, gives you a global type of convergence, this convergence in measure. All right. Now, the rest of the proofs I want to discuss, we are not going to actually walk through proofs. And as we go through them, we'll talk about them briefly. We'll also discuss maybe why we're not going to work through a full proof. The next result that I want to look at is what is known as Egorov's theorem. Egorov's theorem is one of these sort of more specialty theorems where you need to assume a little bit more. In particular, for Egorov's theorem, we need to assume that our domain has finite measure, right? So let me finish erasing here and I'll get this theorem up. All right. So Egorov's theorem says, let E be a set with finite measure, and let f sub n be a sequence of measurable functions on E that converges pointwise almost everywhere on E to a measurable function f. Then the sequence f sub n converges almost uniformly to f on E. Now, again, what I want to highlight here is this is sort of a subclass of these sort of convergence theorems that require finite measure of your domain. Now, there are a couple ways to think of this. One is, well, we work with a lot of functions that are defined on R, so maybe this condition, like, it's not super helpful, right? Well, that's not necessarily fair, because if you think about Riemann integration, we rarely integrated something over all of R, right? In fact, those are improper integrals if you want to integrate over all of R. We were often integrating over some interval, right? And intervals have finite measure. So on the one hand, this is not, a ridiculous assumption to make. And in fact, in many applications, so probability theory is an area highly related to measure theory. And they're often working on spaces that have like measure one, right? Or certainly have finite measure. So there are a lot of applications in which it makes sense only to think about domains that have finite measure. So it's not really an unrealistic assumption, but from a theoretical perspective, it's an assumption you're making. And again, if you want to start trying to integrate things over all of R, or in a higher dimensional setting over all of Rn, this is certainly something you need to worry about. Okay. Now, what I really want to talk about is sort of where this condition comes into play. So we're not going to work through the theorem. If you look in the book has a proof of the theorem, although they don't work with a set of finite measure, they just work with an interval. There are some things that makes a little bit easier to define. It sort of still gives you the same flavor of the proof, but it just makes some things a little bit easier. But what I want to sort of talk you through is why, where this condition that you need the measure of your whole set to be finite, where that comes into play. So what you end up doing in this proof is you sort of define this descending sequence of sets. So you have like E1 and then a smaller set, E2 and then a smaller set, down to En and so on and so on, right? So you sort of have this chain of sets, and these are all subsets of E. Okay. And what you can essentially show is you can show that in a way, and again, you have to make this rigorous, but in a way, every time you go down, you're pulling off some set of positive measure. Okay. And so if you do that repeatedly, the idea is that the thing I'm left with down here, sort of in the limit, this thing ought to have measure 0. Okay. Well, if I start with a set that has finite measure and I pull things off of it, right, then eventually, yeah, I'll pull everything down to 0. But if I start with a set that has infinite measure, even if I pull infinitely many things off of it, right, that are, if they're all finite, I could still end up here with a set that has infinite measure or has, it basically boils down to something like, what is infinity times infinity? Well, it's indeterminate, right? So you actually need the finiteness of the space E in order to make this argument that these sets sort of have to limit to 0. Okay, that's precisely where this finite condition comes in, the finiteness of the measure of the domain. And again, it's something that we see not uncommon in these sorts of convergence proofs, and often it's for precisely that reason. Now, we saw when we looked at examples, right, that we could get some weird things happening. You think about that escaping bump, right? It was sort of a weird counterexample to things. So the escaping bump does not satisfy the conditions of Egorov's theorem because that sequence of functions is defined on all of R, right? So in that case, right, for the escaping bumps, you actually get pointwise convergence, but not almost uniform convergence. So that doesn't contradict Egorov's theorem. It's just that Egorov's theorem doesn't apply there because our domain is all of R. Okay. Now, this is again sort of one of these theorems of the flavor. Okay, I have to assume finiteness of the measure of the domain. But there are also other theorems, and I'm just briefly going to mention 2 others. There's something called Fatou's lemma. So Fatou's lemma says let E be a measurable set and let f sub n be a sequence of non-negative measurable functions on E. Then this tells you something about pushing limits inside of integrals. Now, these are written as lim imps. You can just think of these as limits. The idea is if I don't know anything else about f, right, other than it's f sub n's, other than it's a sequence of non-negative measurable functions, then pushing this limit inside of the integral potentially makes it smaller, right? Now, this is not really a convergence result, but it can actually be strengthened into something called the Lebesgue-dominated convergence theorem. Now, the Lebesgue-dominated convergence theorem actually says a little bit more. So the Lebesgue-dominated convergence theorem says let E be a measurable set and let f sub n be a sequence of measurable functions on E that converges pointwise almost everywhere to E, converges pointwise almost everywhere on E to a measurable function f. Further, suppose there exists a function g on E such that each of the f sub n's in absolute value is less than or equal to this g. So that's the dominated piece, that this whole sequence is there's one function g that dominates all of these functions f sub n. Okay. If that is the case, then what you actually get here is that if you push the limit inside the integral, you actually get equality. Now, one way to rearrange this, right, if this holds, then certainly the limit as n goes to infinity of f sub n minus f, of the integral over E of f sub n minus f, this must be equal to 0. Just pull this over, and you get, you actually get a slightly, you basically get the same thing here. Okay, so really what this is telling me is that if I have convergence pointwise almost everywhere and it's dominated by this, and my sequence is dominated by this function g, then that's enough to say that pointwise implies in mean, right? So this is an example of assume even some more conditions, right? Now you can show that pointwise implies convergence in mean, right? And for many of these, you can show that if you take one of the methods of convergence plus some other hypotheses, you can show that implies another method of convergence. Now, there are a whole host of these theorems, and once you think you understand all of those relationships, there are really other methods of convergence. So there are types of convergence called weak convergence. There are many different types of convergence, and you can start looking at theorems that relate those. Okay, but for today, this is where we want to stop. This has given us sort of a preview of this world of functional analysis, right? And if that's something you're interested in, at some point we may offer an elective in that, or you can just go out on your own and, look for introductory functional analysis texts to learn a little bit more about all of this.